Mike Berman has been, I guess, yes,
the introduction.
That's what we'll do. You see, we're still trying to figure out how to work with the cameras. So Mike Berman's been a program manager here at AFOSR for 23, 24 years. He's one of the guys that I look to as a senior leader in the department, a guy who really understands the kind of full breadth of our science, and excited to have him kick off our group presentations today. Mike is, I've lost count of the number of fellows he is, but he's an AFRL fellow. This last year we were excited to have him elected as an ACS fellow. But I also believe there's a couple other fellowships that I haven't thought of, or I've got my notes over here, but they're not in front of me. So Mike is very active in the professional society. He's a tremendous mentor to all of us in the entire department, and we're excited to have him kick off our briefing. So Mike, here it is.
Okay, thank you, John. And we'll get all wired up here. Thank you. Good morning, everyone. As John said, I'm Mike Berman, and I'm here to tell you about the program that I manage in molecular dynamics and theoretical chemistry. And in this program, we look at issues of energy transfer, energy storage, and energy utilization from a molecular perspective. So we're really looking at fundamental issues of chemical reactivity and energy transfer that underpin much of what goes on in our Department of Energy, Power, and Propulsion. These words on the title, "Energy is Essential to All Air Force Missions," comes from the introduction to the Air Force report Energy Horizons in 2012. And in fact, these are the type of issues that we look at in our program. The underpinning science for energy storage, where we're looking at how to store energy in fuels for propellants, new synthesis, how do we store energy in new molecules, how that energy is liberated, looking at catalytic processes to create new fuels, and do that in a kind of in a sustainable and environmentally benign sort of way. And we look at energy utilization. How is that energy utilized in laser systems, in trying to understand the interactions in the space environment where it's a sparse environment, but it's very reactive. How do reactive species like oxygen atoms interact with spacecraft? What sort of reactive processes? In high-speed vehicles, how do the skins of those aircraft interact with the environment where there's ablation, catalytic reactions going on? Those are the types of things that we want to understand. The energy transfer that leads to heating and limits emissions. We're trying to understand that and feed that back and interact with other communities such as the aerothermodynamics community. So as I mentioned, we're looking at the underpinning science in these areas, and this is what we try to do in the program. We try to address these fundamental scientific issues of energy storage and utilization in these Air Force relevant systems, and really from a molecular perspective, try to develop a mechanistic understanding of these fundamental reactive and energy transfer processes. So a lot that we look at, we'll be looking at these fundamental processes of energy transfer and reactivity. And once we have this understanding, we really want to develop a predictive capability and modeling tools that we can apply to a broad range of Air Force systems. So those are the goals, and the impact on many Air Force systems you can see here. We're trying to develop fuels, propellants, munitions, where we have stored this energy and utilize it when we want. The utilization comes also in high-power lasers, the interactions that take place in high-speed aircraft, many applications, and increasingly moving to some applications in optoelectronics. Now, these are some of the particulars areas that we choose to emphasize in the program. In energetic materials, we're trying to store energy in fuels, propellants, and munitions. And what we look at in energetic materials is really trying to develop novel concepts concepts that really test the limits of how much energy that we can store in molecules and try to understand how far we can push the envelope in terms of energy storage. So this work underpins a lot of what we do in energy storage. Another area that we look at is catalysis. Catalysis is a very high leverage opportunity. It really enables processes to take place that might have been energetically unfeasible because of high energy barriers. Catalysis lowers those energy barriers and makes processes accessible, make them practical. So we're looking at catalytic technologies that help us develop new fuels and propellants, and also utilize fuels in interesting ways too. One process we're looking at are endothermic fuels, where a catalytic process cracks a fuel and enables the fuel to act as a heat sink, absorb more energy than it might otherwise by undergoing an endothermic process. Okay, another area of emphasis is energy transfer. Again, I mentioned high-speed aircraft. As they interact with the atmosphere, there are issues of thermal management, gas surface collisions that heat the surface, catalytic reactions that create new species that couple into the flow. So we want to develop a firm understanding and couple these energy transfer mechanisms with the aerothermodynamics community, incorporating chemistry into the fluid dynamics so we can better describe what's going on in those processes. And finally, we look at extreme environments. Many of the Air Force systems we look at operate in extreme environments. As I mentioned, the reactive environment in space, there are plasmas that form that interfere with communications. So we've got high temperature, high pressure systems, we've got reactive systems, and in many cases it's easier and more accurate to develop simulation methods than it is to perform experiments under those extreme conditions. But we look at both experiments and theory and modeling under extreme environments. Okay, there are many synergies that occur really in the program. The systems that we look at in energetic materials, some of these nanoenergetic clusters, some atomically precise energetic clusters, have the same structure or same size range as catalytic systems that we look at. So there is commonality here in these clusters. The collisional processes that we look at in reactivity are similar to the energy transfer systems. The chemical potentials, the potential energy surfaces that control energy transfer are similar to the ones that we look at in the space environment in those interactions. So there are many commonalities and synergies that tie many of these areas together. And those synergies really cut across not just the scientific disciplines, but the colleagues that we work at within AFRL. Many of the TDs work in this program, and the interactions there, as we bring all of these people together, is also very beneficial. Many of the codes that we develop translate across these TDs as well as they do the scientific areas that we look at. So as John mentioned, much of what we do in this program is fundamental science that underpins work in throughout the rest of this department as well as throughout AFOSR. We've got specific interactions with many of my colleagues, and work that's been developed has transitioned to these other departments. Whoops, maybe I should use this as a pointer. Work, for example, that Keiji Murakuma has done in our program to look at automatic ways to search potential energy surface is now being used in Chipping Lee's program, applying that to combustion systems. work, as I mentioned, on energy transfer, looking at developing the potential energy surfaces needed to describe energy transfer processes and the gas surface interactions. Whether or not excited states are properly treated there is being used in collaboration with folks in John's program on aerothermodynamics. Some electrospray dynamics and graphene catalysts is being transitioned to and interacting with folks in Mitat Birkin's program that you'll hear about, and Dana Dlot's work on laser shocks is interacting now with Jennifer Jordan in our program on dynamic materials interactions. So there are many applications where the work from our program really underpins and transitions its way into other applications, other programs within AFOSR, and externally as well. A lot of the work on the novel energy concepts that we look at really becomes the seed for programs in other agencies as well. So there are a lot of interactions in the programs that we look at. So now I'll tell you about some of the specific scientific challenges that we're focusing on. In energy transfer in reactivity, and particularly in energy transfer, for many years we've been able to observe and increasingly predict energy transfer processes. One of the things we're moving to is being able to control energy transfer. We have some very complex systems that we want to look at in extreme environments. So one of the emerging areas that we're looking at is how we can predict and control energy transfer. In fuels, one of the main goals is being able to store energy in chemical bonds. If you have an alternative energy system, or if you're powered by some electrical process, in the Air Force, we have aircraft that are flying in the air. We don't have long extension cords, so we need to take the fuel with us. We need energy stored in liquid fuels. So we need to try to store that energy, and the best way to do that is in chemical bonds and liquid fuels. To do that in a very benign way, one way we can do this is to store or convert CO2 into JPA. That's an ultimate sort of goal of a carbon neutral type of fuel. One of the keys in doing this is catalysis, as I mentioned earlier. And in these catalytic systems, they often rely on nanostructures as active catalysts. And one of the things that we're looking at is to take these nanostructures, not only use them individually as catalysts, but what happens when we take these nanostructures and put them together to form unique materials? Can we use those nanostructures as building blocks in a way that we can affect catalysis or control energy flow and utilization? And much of this is enabled by advances in the nanoscale recently to be able to predict what's going on in nanostructures, be able to prepare them in atomically precise ways, and probe what's going on. So these developments in the nano world have created these opportunities to use these nanomaterials as building blocks and see what sort of novel properties emerge. And finally, one of the things that we're looking at in the program, what goes on at interfaces. Particularly in these nanosystems, the key processes take place at interfaces. In the introduction, John showed this core shell nanostructure that's being used for enhancing the combustion of methane. In fact, I won't talk about it in much detail in this talk, but the key point is that the active sites of this catalyst are really at the interface between a palladium core and a cerium oxide shell. So it's the interface between the palladium and the oxygen is where all of the chemistry takes place. And so in many electrochemical systems, all the action is at the interface, and we're looking at new ways of probing what's going on at interfaces. So as I said, much of what we do in this program is very fundamental and underpins a lot of other things that go on, but there have been important transitions that have come out of the program. And many of these transitions are the result of sustained investment over 5 to 10 years or more. In the area of energetic ionic liquids, we've really revolutionized the landscape of energetic materials, particularly in making these novel monopropellants based on ionic liquids. Before our program started getting involved in this 10 years ago or so, there really was no work of looking at ionic liquids as propellants. And I'll tell you a little more about one of the important transitions of this type of work. Atomic layer deposition is something that we invested in heavily in developing chemistries for that over a 10-year period or so. And now that's widely used in industry and science, in catalysis, making precision coatings, atomically precise conformal coatings. That's having a major impact in many areas of technology. We're very proud of that. Chemistry codes that have been developed over the years with a lot of work stemming from this program, such as games, which is very, very widely used. ACES 3 now, a version of a coupled cluster software that's the gold standard of high fidelity type of chemistry if you want to get very high accuracy calculations. These are things that have developed with AFOSR funding over many years and become a very important transition to the community. Some experimental instrumentation has also been a very nice transition. This ion mobility spectrometer developed in the laboratory of Mike Bowers at UC Santa Barbara has been transitioned. It's a spectrometer that separates species by their mass and their shape or their cross-section, so you can separate isotopes, and that's been transitioned to separating out some nuclear isotopes and is in use out in the community. Now, one of the particular transitions that I mentioned was ionic liquids and looking at ionic liquids as propellants. Again, something that we invested in over 10 years, and much of this work in the synthesis of these ionic liquids took place out at Edwards Air Force Base, led by Tommy Hawkins, and now transitioned to Stefan Schneider. And they developed this propellant now called Air Force M315E. And one of the nice things about this propellant is that it exceeds the performance of hydrazine as a monopropellant. But it's environmentally benign, it's safe to handle, and as a result, it's been dubbed a green propellant. Minimal impact on the environment and very easy to handle. And as such, NASA ran a search to have what they call a green propellant infusion mission, and this propellant that we developed in our program was selected as the propellant of choice, and NASA is going to invest $45 million over the next 3 years to actually put this into practice, to demonstrate this, to fly this propellant. So it's very difficult to get novel propellants flown in the space environment. It's a very conservative business, but it needs these large investments, and hopefully in 2015 this is going to be able to fly. And we had some very nice coverage over this. Tom and I were interviewed and covered in US News and World Report. And they talk about this propellant being environmentally friendly and safe to handle. And indeed it is. It's being used as the propellant of choice was selected for use as a monopropellant. Here you see maybe some artistic license and showing it as a bipropellant application. But in fact, they're getting just a little bit ahead of what we're actually going towards looking at those bipropellant applications. Work currently going on at Edwards Air Force Base, led by Stefan Schneider, is looking at hypergolic ionic liquids, these bipropellants where you can mix this ionic liquid with an oxidizer, it bursts into fuel right away. And for bipropellant applications, you want a lot of hydrogen given off. So they're looking at these novel alumino-cyano-borohydrides, lots of hydrogen in these species. And in addition to just the synthesis of these novel propellants. We're also looking at the dynamics. What are the properties? How can we predict the properties of ionic liquids? There's been a lot of work done over the years in that area. Jamie Stearns at Kirtland Air Force Base now has developed some novel spectroscopic methods looking at what's going on in the vaporization of these. Ionic liquids have the nice property that they have very low vapor pressures. That's what makes them a lot easier to handle. But there is still some vapor that can be coaxed out of these, and the folks within our program are identifying what are the ionic species that come off, whether or not things come off as ion pairs, what sort of clusters come off, some novel breakthrough science going on there. Now I'm going to tell you a little bit about some of the work that we're doing in creating novel ways to make sustainable fuels. Many Air Force reports have identified the need for having alternative fuels and creating them in sustainable ways as a key to the future. And so one of the most sustainable ways that we can do this is if we can chemically reduce CO2 and turn that into a useful fuel, turn that into jet fuel, CO2 to JP8. And to do this, catalysis is the key. Many of these processes can be done, but at some cost. What's the energy cost for doing this? And what catalysis does is lower the energy barrier for doing this. If you look at doing this with just a metal alone, there's a high barrier, but with a particular catalyst, you can greatly reduce the energy barrier, making this a feasible sort of process. So we're looking at three ways of addressing this problem. One is an electrochemical catalysis to form syngas, CO2 to syngas, which is a combination of hydrogen and CO, which can then be converted into gasoline. Heterogeneous catalysis that can form higher alcohols. We can go directly into something that we can burn, like methanol or butanol, propanol, other alcohols, or some homogeneous catalyst that can reduce CO2 as opposed to a heterogeneous catalyst. The homogeneous catalysis is, and much of this work that I'll mention is work of a Muri that we have in this area of CO2 reduction led by Cliff Kubiak at UC San Diego. And I won't go, I don't have a slide on this, but the key point that they've been able to do in this work is from a very atomic perspective, understand what orbitals are involved in the active state of the catalyst and how those lead to interaction with CO2. And by identifying those orbitals that were playing the active role in a rhenium catalyst, which is a very expensive metal, they've been able to say, can we take something with the same electronic structure and get the same catalytic results? And in fact, they were able to do that by using, instead of rhenium, using manganese, which is a much more earth-abundant material, much less expensive. So by this fundamental understanding of what orbitals are involved in the chemistry can lead to making this a much more cost-effective process. So now I'll tell you a little bit more detail about the work that's going on in taking CO2 and converting that to syngas. This is done through an STTR program with a company called Dioxide Materials. Rich Mazel is the lead of this company. And again, they've used an ionic liquid as a co-catalyst to work along with a platinum surface to greatly reduce the energy barrier for this process to take place. It now goes to CO2 to syngas, this 3-to-1 ratio of hydrogen to CO, with about 80% efficiency and very high selectivity. And that syngas can then be turned into gasoline by a Fischer-Tropsch process. And by controlling the pH of this process, they can control the ratio of hydrogen to CO. Within this STTR, with the help of Dana Delott, they're going to be looking at what is actually going on in the surface of these electrodes, using methods like some frequency generation to probe what's going on the surface to see whether or not the CO2 is complexing with the ionic liquid in a way that's reducing the barrier here for this process. Another approach that we're looking at is CO2 directly to alcohols. And this work was motivated by work of Andy Bucarsley at Princeton University, been demonstrated a number of years ago, and now being looked at in more detail with electrodes such as this gallium phosphide, but also a wide range of other electrodes as well, platinum, many other metals. And it does turn out that there's a key role that both the electrode plays in this process, as well as pyridine. Pyridine is, again, a co-catalyst here, and we're trying to understand the mechanisms of how this takes place, again, to see if we can enable wider use of this. So within this MURI effort, Emily Carter and her colleague, particularly a postdoc named John Keith, who's now at University of Pittsburgh, did a study of what was the mechanism of this process, and they found that one of the first steps of this process that was originally proposed, pyridinium going to a pyridinyl radical, was really energetically unfeasible. That couldn't be the process because there was much too high of an energy barrier. They did a very detailed study on this. And so another group, Victor Batista at Yale, looked at alternative mechanisms. And what Victor has shown is that perhaps the pyridinium is acting as a shuttle, bringing hydrogen atoms down to the surface, and then participating in a proton-coupled electron transfer that can reduce CO2 with a much lower barrier. But again, what's key is what's going on the surface, what's going on at that interface. And again, Tim Lian is part of a team that's going to use some frequency generation to look at these intermediates on the surface, this real-time probe of these electrochemical processes. So Tim Lian from Emory is going to be looking at that along as part of the MURI. Nate Lewis will be using differential electrochemical mass spectrometry, or DEMS, to look at these surface interfaces. Okay. A lot of that are some of the highlights that we've accomplished over the last few years or so. As we go into the future, I wanted to tell you about some of the programs that we'll be looking at through BRI topics. We've been fortunate enough to interact with a number of colleagues throughout AFOSR and be involved in some basic research initiatives. And I'll tell you in a little more detail about a few of them. One is the foundations of energy transfer, and a highlight from that, where we're looking at energy transfer and particularly trying to couple that with the aerothermodynamics community. We've got radical species and very reactive species. Some of that also takes place in the plasma surface interactions. We're looking at ions and radicals and atoms interacting with surfaces, understanding some of the details of that chemistry. But I'll talk about this energy transfer a little bit, and these novel building blocks, nanoscale building blocks for novel materials, and controlling energy transfer pathways. So in the energy transfer highlight, this is work of Bill Haase from Texas Tech University. And he's trying to model, using chemical dynamic simulations, the interactions between this molecule here, carbon hexafluoride, and nitrogen. And typically, if a chemical dynamicist would study these interactions, they'd do trajectories of this C6F6 molecule interacting with a nitrogen and sum up many of these trajectories and try to put together the overall picture. But because Bill has been interacting with some of these BRI teams, and there's really this community that's been developed between the chemists and the aerothermodynamicists, Bill Haase has really taken some things from the DSMC, or direct simulation Monte Carlo methods, that the aerothermodynamicists have used, and used that as inspiration and said, okay, instead of looking at those individual trajectories, we'll just take this molecule, put some energy in it, and then put it in a bath with many of the nitrogens and let these calculations run and see how this energy dissipates. And the nice thing is in these calculations, Bill has done high-level ab initio calculations to get the interaction potentials, to do the chemical dynamics. And from this, he's found that the energy transferred per collision that he can simulate agrees quite well with experiment, but it conflicts with or calls into question a commonly used model in this energy transfer field. That's what's a model called delta E down that says there's a particular energy per collision that can be used throughout the energy regime. And Bill finds as much larger energy transfer per collision at higher energies and smaller amounts of energy transferred at low energies. But these types of simulations and this type of interaction is the type of things that the chemistry community is bringing to the aerothermodynamics community, and hopefully it can be incorporated into their simulations. Now, nanoscale building blocks is something that really stems out of our interest in catalysis and energy transfer, being able to control energy flow. And we have many of these nanostructures that have been used individually, but questions arise as to what happens if we put these nanostructures together. Can we build them into lattices, and can we control how they interact? Can we use them as novel building blocks? And many questions arise as to what can be done with these. So basically, over all of the years of history, when we've made lattices or structures, we've composed them of atoms or molecules and bound those together. But now we have the novel opportunity, instead of just using atoms and molecules as our building blocks, can we use nanostructures? Can we use something like this energetic nanostructure and make lattices based on these bound or linked together? This is an atomically precise aluminum cluster. Or can we use a catalytic nanostructure like a metal nanoparticle as a building block, or a quantum dot with particular electronic properties as a building block? And can we link them together in novel ways that control the coupling between these? So we've got lots of different handles that we now can adjust to control the properties of these materials. And I'll tell you about some things where here we're looking at electronic properties or optical properties of a system, where we take 2 nanocrystals or quantum dots, where typically the electrons would be confined to that structure. But now if we put a linker or a coupling agent between the two, the electrons can now leak between those structures. So the electrons are not confined the same way that they were before. And as you can see, you can control the electronic properties maybe in a different way from the mechanical properties. You can decouple the electronic and mechanical coupling between these to lead to thermodynamic, thermoelectric materials, or ways that we can control thermal conductivity. And we've got novel ways that we can look at mechanical structures as well. So there are many applications of the electronic coupling. As we change the coupling strength, we can find many different electronic properties arise. We can control the optical properties. We can control catalysis as we get more coupling. We can get thermoelectric materials, even computationally interesting materials, or mid-infrared cameras, all as a function of these coupling strengths. So these are some of the things that we hope to explore in this type of BRI. And here's an interesting example of some of the unique materials that can emerge as we use these atomically precise clusters as building blocks. So this is work. The synthesis is done by Terry Bigioni at University of Toledo, and the theory, Uzi Landman, who's part of our program. And they've made lattices of, or large amounts of ultrastable silver nanoparticles. So these are the structures. It's got a silver 44 core, and you can bind these together as in stable lattices, and the electronic structure tells us why it's stable. It's an 18 electron system. So that means that in a superatom or jellium sort of model, if you've got 18 electrons available. It's a very stable shell. So it forms very stable geometric structure as well as an electronic structure. They've been able to develop the first crystallization and X-ray structure of these particles, and we've been able to provide some of these samples ahead of time to some AFRL scientists. But an interesting thing happens as this material forms the lattice that's really controlled by hydrogen bonding of these para-mercaptobenzoic acid ligands. That as you compress this material, there's some discontinuity. You can compress it to a particular compression, and then there's a drop over here, almost a phase transition, a change in properties. And you'll see what happens as we look at this crystal structure that we have from the simulation. As we begin to compress that, now each click is compressing this further and further, you see all of a sudden the lattice start to change. And these ligands that help form the lattice are buckling and providing an interesting energy dissipation mechanism. So it's an interesting mechanical property that's emerged from these lattices that we have from these nanostructures put together. That can give us an interesting energy dissipation method. And this material has a negative Poisson ratio. When you stretch it, instead of getting thinner, it expands as a result of kind of these kinks in these ligands as we compress it. So interesting materials. Finally, one of the things that we're looking at in energy, being able to control energy transfer arises with some motivation from photosynthesis and natural biological systems. Can we do molecular engineering to control and optimize energy transfer in materials? And part of this is because materials like solar cells or other optoelectronic devices, infrared sensors, can be limited by getting electrons out or moving excitons through these materials. And in photosynthesis, in nature, where light can be harvested through antenna structures and then go through many hops, 10 to 1,000 hops, before it gets to its active site in a catalyst. Nature can do that very efficiently, 10 to 1,000 steps with 100% transmission efficiency. We'd like to know if we can be able to do that. And one way that we've seen recently is natural systems, photosynthetic systems, have been demonstrated to demonstrate coherences. These coherences have been observed to live much longer than expected. They live for picoseconds or so. And what's important about that is they live on the same time scale as the energy transfer processes. So you'd be able to think that maybe we can be able to control energy transfer. It's observed that it makes energy transfer more efficient. So we'd like to see if we can be able to control this. We've got methods to try to observe what's going on with two-dimensional spectroscopy that lets you see the couplings, or what states are involved in the coupling. So these are some of the things we're trying to observe. And we can demonstrate that we can use this as a design principle in a simple way. These are some calculations by Greg Engel, but it just shows how can we, what's the optimum way in which we want this material to interact with this environment. What we show here is coupling between the material and its environment, the phonon modes of the environment. If we have very weak coupling, we can excite this molecule, but the energy won't transport. It's not coupled well to its environment. So as we increase the coupling, we improve transport. But if we go to the extreme of very strong coupling, then that energy no longer stays in the molecule. We can't absorb energy in the molecule. The oscillator strength is spread out in the classical view. So we have to reduce the coupling to improve the excitation efficiency. So there's an optimum coupling over here. So it's a design rule that we can use the interactions can't be too weak or too strong. They've got to be just right. That's why they call this quantum Goldilocks principle. It's just got to be just right. So it's a tool that we can use to optimize the energy transfer. And these are some of the things that we're going to try to do to utilize coherences. We can try to use nanostructures also to control the energy transfer. Martin Zanni and Mike Arnold at Wisconsin are using nanotubes where you can get ballistic energy transfer through the nanotubes to get very fast and efficient transfer and guide energy flow from moving from nanotubes with higher band gaps to lower band gaps, so we control this energy flow. Emily Weiss has also demonstrated that you can do vectorial energy transfer, control the flow by also going to smaller band gaps in quantum dots. Have small quantum dots, medium size, and larger ones that direct the flow of energy. You can funnel energy flow. So those are some of the things that are emerging in directions that we're trying to pursue in terms of energy transfer. So we use these clusters, nanostructures, and plasmonic systems to try to control energy transfer. We have a very successful program in this area, and hopefully looking for more exciting results. Thanks.
Any questions or comments for Mike as we're transitioning to our next speaker?
Earlier in your talk, you mentioned that the extreme environments. In your research, what are the environments you are considering, like pressure, temperature? Do you have high gravity, microgravity, radiation? Do they play any role in your research?
So the extreme, the question is what sort of extreme environments are we looking at? Particularly, we're looking at plasma systems where it's very reactive, and we've got ionic species. We're looking at systems where radicals are present in great extremes. We're looking at high pressure, high temperature systems, particularly in catalysis for endothermic fuels. In fuel systems, you've got very high temperatures and high pressures. So we're looking at chemistry under those conditions. Can we catalytically break down fuels without coking? We're looking at, in some cases, ultra-cold chemistry. One of the BRIs is with Tatiana Kirchik, where we're looking at fundamental chemistry at very low temperatures, millikelvin temperatures, where you can freeze out all thermal motions and just look at the fundamental long-range forces that are controlling chemistry there. So those are some of the extreme environments that we're looking at.
So no gravity or radiation?
We're not looking at per se, although some of the theoretical methods that we're looking at, for example, can play a role in looking at radiation chemistry. We're looking at, for example, we have a YIP program looking at relativistic quantum mechanics and using relativity when we look at spin-orbit coupling and looking at optical transitions. So that's something that can be applied to radiation and the kind of the optical transitions that can be initiated that way.
Thanks, Mike. Let's go ahead and transition to our next speaker.